Hey, welcome back, my best chemistry students. And we are from Allen High School. So this is copyrighted Allen High School. Not sure what that means, frankly, but we have the copyright at Allen High School. But I welcome all viewers who can put up with this without falling asleep on me, as some of my students have been telling me that they fall asleep. And the good news is at least you can rewind me when you wake up. Now, we're talking about the atom. We're in chapter 4 of the elusive little electron. That's my book of notes that I use. And we're on the second video of that. And we're going to do a little introduction to components of an atom. And certainly we are not going to get at subatomic particles like you would do in a physics class. We are going to keep it very simple. And I'm also going to be putting videos of this online from pre-AP. So if you want a little bit of a review of what we did in pre-AP chemistry, those should be going online very quickly as well. So we not only want to look at those main components of an atom, we will be focusing on the proton, the neutron, and the electron. But we also want to look at the effects of changing the number of each of these. And this is actually going to allow me to bring in a little bit of nuclear chemistry without having a full-blown nuclear chemistry unit. So let's forge ahead and take a look at protons. So the symbol we'll use, or that you will often see for protons, is a P. It has a charge of 1. We typically don't put a plus there. And it has a mass of 1. So this number here is going to be either the atomic number or charge for a particle, not an ion charge, particle charge. If it was an ion, we put it up in this area here. So it's a particle charge. That's a lowercase p, and it has a mass of 1. So these are your positively charged particles in the nucleus of the atom. This is their mass in atomic mass units. It's a relative scale. I'm not going to get into it too much. We don't use atomic mass units for very long. Very quickly, as we've already done in our other units, we start to talk about grams per mole instead. But in an absolute mass value, we're looking very, very, very tiny. So those are the kilograms, 1.673 times 10 to the minus 27 kilograms. Remember, kilogram is our SI unit. So that's why those are reported in kilograms. Now, the key aspect of a proton is it's the protons that define the identity of a substance. If you change protons, you no longer have the same substance. And the change in number of protons is going to happen as a result of nuclear, whoa, I didn't spell that right, nuclear reactions. Now again, we're only going to have time to touch on nuclear reactions. This is such a fascinating unit to me, especially as we read in the paper the discussions of nuclear power plants and what we do with spent fuel, and we see what happened in Japan. I think it's a very good topic to wrap your minds around. I wish we had more time. Maybe after the AP test, we'll take a day to look at that. Now, we sometimes call this a transmutation, especially if it's accompanied by more than one step, because what's going to happen is that unstable nuclei, we'll see in a minute how we know that they're unstable will decay. And if it decays to an unstable, it's going to decay. And then the next will decay. And these are all going to decay until finally a stable isotope or nucleotide, not nucleotide, stable isotope is found. All right, so the periodic table is arranged according to the number of protons. I would hope you would know that by now, not mass, but by the number of protons. So let's take a look at this. We're looking at the change. That delta, remember, means change in the number of protons. And this is a graph that gives us a guideline. So if you notice that axis, the x-axis is our number of protons, and the y-axis is our number of neutrons. And what scientists have found is it seems to be that ratio between our number of protons, or excuse me, our number of neutrons and our number of protons that gives an indicator of stability. Now, if we're at very low elements, such as carbon, so our most stable isotope of carbon is carbon 12, we would indicate that with either a hyphen 12, or we could put it with a C, and we'd put a 12 in the upper left-hand corner. Now, the most stable isotope, and we'll get back to isotopes. I know I'm using a word we haven't talked about yet, but we'll get there. The most stable is with carbon 12, and we have 6 neutrons, 6 protons. So it seems that down at the low end, we're looking at a 1-to-1 ratio. Now, the radius of a sphere goes up dramatically, or the volume of a sphere goes up dramatically with radius. So as we get into larger numbers, and actually really up to 83, because past 83, they're all radioactive, we can handle maybe, I say we, elements can handle about a 1-to-5 ratio. Now, on this side, what we find is that we have too many protons, or excuse me, neutrons. Too many neutrons. There's my mind ahead of my mouth, ahead of my hands again. Sorry about that. And down here is where we have too many protons. Too many protons. And out here, they're just too big altogether, as we'll see. And so those are going to undergo some sort of decay process to reach stability. Now, I want to look at each of these particles because you need to know what they are. If you see beta, or you are told that it is a beta decay, you need to know what to write for a beta particle in a reaction. Likewise, if you see alpha, you need to know what to write. That's simply a symbol. In a chemical reaction, we have something different to write. So let's take a look at each one of those. Now, here I had a loss of integrity in my PowerPoint as I brought it into my Mimeo. I guess I'll be working on that technology soon. Now, this is alpha decay. In this decay, you lose the equivalent of a helium nucleus, and that means we're losing 2 protons and 2 neutrons. So that helps for things that are, substances are just too big overall. Now, technically, it has 0 electrons, but do you notice that scientists don't put a charge in that upper right-hand corner? It's understood that when we're talking about an alpha particle, that it is stripped of electrons, that it's coming from the nucleus of the atom. Now, these aren't hard at all because the mass numbers on top and the atomic numbers on bottom have to be equal on both sides of the reaction arrow. So all you have to do is say, well, what number plus 4 is 238? Well, it's 234. Double check that. 234 plus 4 is 238. Then we would have 90 plus 2 is 92. Then you look on the periodic table to find out that that's actually thorium. Now, you notice on this that the resulting isotope, nuclide here, has a decreased mass relative to what it was. So from what it was to what it became, it's decreased the mass by 4, and it's decreased my atomic number by 2. Notice, change in the atomic number here means that we have a change in the identity of the element. It is no longer uranium. It's a brand new substance. And this would continue until stability would be reached, which could be tens of thousands of years. Now, let's do the next one. Beta decay. Again, sorry about these little arrows here. There, that should be an arrow. Beta decay is the loss of an electron. But we're not talking about those valence electrons or those outer electrons. we're talking about a nuclear electron. I know that sounds a little odd. You might not be familiar with that. Hopefully you did talk about it in physics. But what happens is that a neutron in the nucleus, mass of 1, charge of 0, splits into an electron. In other words, a negatively charged particle with a negligible mass, which is what an electron is. And we call that a beta particle. You should memorize that. You need to know that. Now, what plus 0 is 1? 1. What minus 1 is 0? Plus 1. Well, that's a proton. And so if we look over here, it would be 14 plus 0 is 14. Remember, we're making the numbers equal on both sides of the arrow. And then it would be 7 minus 1 is 6. Element 7 is nitrogen. Now, in this case, my mass number is the same. And my atomic number went up by 1. And I'll tell you, I don't memorize this. I'll just make up some numbers. If I want to find out what happened to my mass number and my atomic number, I would just make up a number. I'd put an X, and I'd put a 50, and I'd put a 25. I just make it up, and then you'd put a 0 and a minus 1, and then I'd say, oh, let's see, that should be 50, that should be 26. Oh, I guess the mass number stayed the same, and my number of protons went up by 1. So that's how I do it. I usually just try to figure it out, all right? And so that is our beta decay. And the next one that we saw was positron. Positrons are interesting little particles. You will often see the symbol beta plus for a positron. You may even see beta negative for the regular beta particle. And hopefully you won't see a typo. That's the typo. The positron has a negligible mass, much like an electron, but look at the difference. It has a positive charge instead of negative charge, hence the word positron. Now, in this case, a proton, 1 and 1, emits the positron and forms a neutron. So that's what happens. That stays, that flies out of the nucleus. And here's our arrow again. And what plus 0 is 18? 18. What plus 1 is 9? 8. Look at your periodic table. What's element 8? Well, element 8 is good old oxygen. So that's how we work that one for positron decay. And in our next video, we will be looking at changes in the number of those outer electrons. Pretty straightforward, something you know already. We're just, for completeness sake, I like to cover that right here too. So